Hello and welcome to the lecture. And in this course, we are moving ahead to understand the discrete time representation. Now, before we begin the discrete time state space representation, we would look into the discrete time frequency domain representation once. So, there we would come into the understanding of the Z transform, and we would see how this is utilized in the frequency domain representations. And so let's move ahead. So let us first understand how a discrete time system looks like. So whereas you can see actually the plant is mostly a continuous time system, because the plants or the systems that we know of, like the mechanical systems or electrical systems or some other systems, so you know that the internal variables and the output are continuously evolving with time. So it is a continuous time system as such. However, due to the presence of computers and microcontrollers, so nowadays in the modern times we have shifted from using an analog controller with those analog circuits and those dials and all. So we have shifted from using those controllers to using computers or microcontrollers, where we can actually implement the controller as a digital code, and as a code which actually gives rise to some discrete pulses. So, and these discrete pulses are further converted in the something called the digital to analog controller and the whole circuit, and it is made continuous time, and that is fed to the plant. So as you see in the total block diagram, let us start from here. So we have the output, and we take the error from the reference, and this error is sampled. So this is the first discretization operation that happens. So it is sampled. So we don't record the continuous variable et. So we sample it at definite times, and then after sampling we pass through an ADC, which is an analog to digital converter. So after sampling also, it has some value uh, which is then converted to a digital word. So digital word it is converted to using the analog to digital converter. So some value is converted to the digital word, then it is passed through a computer, and here the entire control calculation operation happens using the input digital word, and then it outputs also a digital word, and that digital word is getting converted to some analog value, and that analog value is getting hold for some time duration, which is exactly equal to the period of sampling. So during that sampling period, whatever analog value is thrown out by the DAC, that is getting held by the hold circuit, and here you obtain a continuous signal which the plant is fed with. So here you can see the complete block diagram, and hopefully you have understood where the discretization happens, and where the digitization happens. So there are few things. So there is the first thing is the discretization, and another thing is the digitization. Both are separate. So discretization happens when the sampling takes place, and digitization happens when the analog to digital conversion takes place. Then this is entirely in the digital domain, this operation. So there are some computations happening using binary numbers. Okay, so using zeros and ones the computation happens, and then from digital to analog, so you get a I cannot say analogization, but it is like that. So you convert the digital word to analog, and the analog conversion happens, but that is not the continuous signal, it is simply a value, it's simply a value. When that value is held for a specific time, so certain value, this is, suppose this is a 0 mark, some value is held for a particular time, then the value changes suppose to another value, and this is how the UT signal gets generated. So a particular analog value is getting generated from the digital world, and it is getting held for certain time instant. So this time period it is getting held, and this time period is exactly equal to the sampling period. So there is something called the sampling period in this entire system. Normally it is denoted by tau or capital T. So one of these symbols are used. Now what are the features here, why we are going for this discretization digitization? Because it can handle multiple inputs, it is easily reconfigure, all these points that has been mentioned here, these are the points in favor of digitization, in favor of using a digital computer. It is easily reconfigurable program for control computation. Suppose you have made a hardware for PID, it will remain a hardware for PID control. But if you are having a digital computer, suppose you implement a PID control, you don't like it, you can go for some other control. There are many other control strategies. So you can go for any such control strategies. So you simply have to write the code and flush it into the microcontroller or into the digital computer. So it is easily reconfigurable. High degree of accuracy, this is very important, high degree of accuracy both in measurement and transmission of data. Now you already we have discussed, we had discussed in the digital electronics course that using why we are going for the for the digitization, why we are using binary numbers for computation, why we are not using the analog signals for computation, because the analog signals are not accurate. So if you are thinking of 5 volts, you will not get 5 volts, you will get something around 5 volts. But if you are thinking of 5 in a binary word, it will always be 5, it will not be anything else. Okay, so there is a high degree of accuracy both in measurement and transmission of data also. So during transmission, binary words are less affected by the load conditions, whereas the voltage signals or current signals would be affected quite a lot by the load conditions and the conditions of the transmission line. So this is a very important point in favor of sample data control system, or the discretization and digitization of the entire control system. This actually, this loop is called sampled data control system because the data is sampled. So the data which you are using for computing your control action is sampled, so it is called sampled data control system. Reduces the power demand because you are only using transistors and all with very less power demand, and many signals inherently available as discrete. This is a offhand feature. So this is basically what it is saying, that sometimes the plant is of discrete nature. Sometimes the systems are such that the signals available from them are in discrete time pulses. Suppose you can check that radar systems are such systems, and there are many other such systems. Examples are not coming to my mind right now, but these sort of systems are sending off its output signals in not in a continuous fashion, but at discrete discrete instants of time they are sending out its output. So these are some systems like that. This is sample data control system, and now we look into each of these components. Actually, some of these components we'll basically look into the sampler and the ADC and the DAC and hold circuit. So the sampler and the ADC, so these are two different things. Please keep in mind. So the sampler is what samples a continuous signal. So the sampling instants are, suppose these 10 units of time, 20 units of time, 30 units of time. So these are not second, these are any unit of time. Mostly they are microseconds, in the range of microseconds. So the sampling is done at 10 microsecond, 20 microsecond, like that. So what is the value at 0? This is the exact value you see given by the black dot in figure B, and exactly at 10 this is the exact value. So in this way we are sampling the signals. In the sampling, how does it happen? We basically multiply a continuous signal with a train of pulses, with a train of impulse. Okay, so the train of impulse is mathematically represented as this. I hope you remember from your signals and systems class about this representation of the signals. So this is the train of impulses. Now of course you will tell me that we cannot generate impulses in a practical situation. Sure, these are not impulses, these are unit steps of very small width. So the very small width pulses. However, for the purpose of mathematical representation, we represent it with as impulses. This is an approximation. Of course, this is an approximation done, but this eases the mathematical computation greatly, and with not any appreciable loss of accuracy in the mathematical representation. So that's why we do this. We use the impulse train. Mathematically we are actually we are sending pulses, very short duration pulses, but mathematically we can represent them as train of impulses, and we are multiplying the train of impulse with the actual signal. So this is called pulse amplitude modulation. Pulse amplitude modulation. So you are getting the amplitude of the pulses modulated by this continuous signal which you are actually trying to sample. So this is what happens, and then what you get as a result is a pulse amplitude modulated signal. So the pulse is modulated by this amount at every time instant. So this is what is happening. So this signal you are getting. So this is exactly what happens in the sampler. So this is about the sampler. Now this sampler is basically this quantizer. No, after sampling. So here the sampler was there. So here the sampler was there. And after that you are getting this output. Now you are passing this output through something called the quantizer. Now you notice that these values can be any arbitrary value. These dots can be any arbitrary value. But if you are trying to use binary words for computation, binary words has a certain quantization, has a certain quantization level. That means between two uh, between two words, uh, so like if you divide the entire range of 0 to 5 volts, suppose 0 to 5 volt you are trying to divide with a 4-bit word. How many 4-bit words can be there? 2 to the power of 4 minus 1, right? So then you are getting 16 minus 15. So 15 different levels you can get. So 0 is of course one level, 0 0 0 0, and this is the final level 1 1 1 1, and in between you can have 15 divisions. So there is something called the quantization. So the quantum of level jump is 5 by 15, which is 1/3. So every new word that you get, so between every successive word there is a gap of 1/3 volt, 1/3 value. So you cannot actually, what is the point here? The point here is that you cannot have any arbitrary value being fitted by a binary word. You cannot have that. So what to do? We have to quantize the analog value. We have to quantize the analog value. Quantization of analog value means to shift it to the nearest binary level, to shift it to the nearest binary level. So suppose you have a value which is something which is 4.9. So you cannot have 4.9 here, so you have to shift it to 5 and then get the binary word as 1111. Similarly, if you have, this is 1/3 is basically 0.33. So suppose you have some value of 0.87 volt, then 0.33 is 0001, 0.666 0010, then 0.99 is 0011. So you will shift it to this, the nearest level you will shift. So there are different methods of quantization. Normally it is nearest level. Okay, so nearest level quantization means you shift it to the nearest level. There is also ceiling quantization and floating quantization. So ceiling quantization means shift it to the immediate upper level, and floating quantization means shift it to the nearest lower level. So here, as you can see from this picture to this picture, we have done nearest level quantization. So every value is shifted to its nearest level. So as you can see, these two points are shifted to the same level. Okay, so though they are very far apart in analog value wise, they were far apart, but after the quantization, you see, they come to the same level, they become the same value, they become the same word. Okay, so this is what happens actually in the quantization process. So after the quantization, what you have to do? See, this quantization, now after the quantization, first thing is that they are having some value, they are still not words, so you have to assign a word to this value. So now you have to do an encoding of these values to binary words. So the value that you have, it passes through an encoder and it gets converted to binary words. So this is the entire process. So first sampling, then quantization, and then encoding. So after that you get the string of binary words, and then you feed the binary word to the digital computer, then you do some computation as per whatever algorithm you have coded in there. So then it gives you a result which is also a binary word. Now this binary word cannot be fed to the continuous time plant, so you have to go through the DAC and hold circuit. So what does the DAC and hold circuit do? That we'll see, but before that there is an important thing that I missed. So that is the sampling theorem. So here you see this signal that we generate. So this is the sampled signal, this is the sampled signal. So I have changed the variable to x here. So this is a sampled signal, and if you take the Fourier transform of the sampled signal, is the Fourier transform of the sampled signal, then it is basically, if you do a Fourier transform, you will see that your XSF is going to be like this. Okay, so this is your XF, and this is the Fourier transform. So actually there are two things. One is the unsampled signal. So one is the unsampled signal. You have taken the Fourier transform of that and you are getting XF. Then is the sampled signal and you are doing a Fourier transform of that and you are getting XSF. Now what is the relationship between XF and XSF? That is my concern. So since I know the unsampled signal, I can do the Fourier transform and collect the frequency information in the Fourier transform. What does the Fourier transform gives? It gives the frequency spectrum. So this is the frequency spectrum. So now after sampling, my objective is I should not sample in such a way that the frequency information is lost. I should be able to recover the frequency information, the frequency spectrum of the original signal even after sampling. That is the objective. So for that, I have to find out the relationship between the Fourier transform of the sampled signal and the Fourier transform of the unsampled signal. So that relationship, from these steps, you find out that your sampled signal, the Fourier transform of the sampled signal is equals to this summation k minus infinity to infinity of xf minus kf. So xf is the Fourier transform of the original signal, and that is shifted by this amount, and this k is varying. So that means you will see a repetition. You will see a repetition of the spectrum over the entire frequency range. So whatever was limited to minus f max and plus f max now is spread over the entire frequency range from minus infinity to plus infinity. It is simply a repetition with some scaling. So this scaling is already, it can be obtained very easily. So this scaling, this is the pulse strength of the impulse, and t is the time sampling period. So these are known information. So what is important to note here is that the original frequency spectrum of the unsampled signal is getting repeated over the entire frequency range from minus infinity to plus infinity. Now the sampling theorem, Shannon's sampling theorem, says that if you have your sampling frequency capital F, this capital F is sampling frequency, by the way. So this T is the sampling period. So capital F is the sampling frequency. If your sampling frequency is greater than twice the maximum frequency of the Fourier maximum frequency of this original signal, then you would be able to recover the Fourier you will be able to recover the Fourier transform, that is the frequency spectrum of the original signal from the Fourier transform of the sampled signal. So this is the Fourier transform of the sampled signal in the condition where f is greater than twice f max. And here you can see that these repetitions of this Fourier transform is happening in a separated manner. So that means you can actually fit a low pass filter, and with the help of this low pass filter you can segregate out this particular portion only. Okay, and that gives the entire frequency information. However, if your f was less than twice f max, then there will be some overlapping. Happening, and then if you place a low pass filter, no matter what low pass filter you use, you will not be able to get back the original spectrum. So this is the Shannon's sampling theorem, I hope it is already covered in your signals and signals and systems class, but we have a revision then. So there is no proof in this course for this particular theorem, so this is what you need to maintain. So after the sampling theorem comes the so the sampling theorem was regarding the sampler. So how frequent you should sample, that is given by the sampling theorem. And then comes the zero order hold. So this is the part of the DAC and hold circuit. So the digital word is converted to an analog value. That analog value is a direct conversion, or some way it is converted. It can be like direct conversion is the easiest one. So after that, what you are having is some analog value levels. You see, they are in specific discrete levels. Okay, but it is just 1 point, because you are calculating your computation is happening at this instance of time, which is the instance of time separated by the sampling sampling period. So the computation happens at specific instance of time which are separated from each other, and the separation is equals to the sampling period. Now what we should intend to do is extend this value throughout this sampling period. That is what our intention is. So you see, this value is getting extended throughout this sampling period, this value is getting extended throughout this sampling period, then there is a change in value, and that is also getting extended throughout the sampling period. So this is how the zero order hold works. The zero order hold simply holds the previously generated analog value. The previously generated analog value it holds for the entire period. So that is the functioning of the zero order hold. Okay, so you read this portion where you have several points regarding zero order hold. Like you can see that there is high frequency signals are there. So here there is a rapid jump between the signals. So this is very high frequency jump is there, but these high frequencies are filtered out by the system itself, because systems inherently are low pass in nature. So these high frequency signals do not matter. Then in first order hold or other higher order holds, what happens, the last two, in first order hold, the last two sample values are used to reconstruct the signal. Similarly, in for higher order holds, several previous samples are used to reconstruct the signal. How exactly they are used to reconstruct the signal, what is the exact formula, we don't need to know for the purpose of this course, because zero order holds are the ones which are used basically. And why? Because these first and higher order holds offer no particular advantage over ZOH. So if you use a ZOH, which is the simplest order hold, zero order hold, in conjunction with a high sampling rate, then this provides satisfactory performance, as has been observed in all practical systems. Zero order hold in conjunction with a high sampling rate provides satisfactory performance. And nowadays sampling rate can be very fast actually, because your transistors have been very fast, processor speed have been very fast, so in range of gigahertz also. So the sampling frequency, there is no issue with sampling low sampling frequencies actually. So this is about the generation of the analog generation of the continuous analog signal, which is now fed as the control signal to the plant. Now comes the story of ZTransform. So after we understand how exactly the sample data control system loop works, and the exact working of the sampler sampler circuit, sampler and ADC, and then the DAC and ZOH circuit. Now we come to the understanding of how we are actually going to analyze these sample data control systems. So the analysis can be in time domain, the analysis can be in frequency domain. So the first we would understand the frequency domain analysis, and we will not be going into too much depth in either of the frequency domain or the time domain analysis, because normally normally when we are designing control systems, we actually design it in the continuous time model. We design everything in continuous time using continuous time models, and then simply apply it through a sample data control system with keeping the sampling frequency very high, and that gives us the equivalent performance, almost the same performance as expected from a continuous time control system loop. Okay, so we normally don't invest so much time in understanding the discrete time analysis, but some understanding you should always have. So this is what we are presenting, the Z transform. So suppose a sampled signal is there. Now this sampled signal is simply the sampled signal. It is not been quantized. Okay, so it is simply some values. So if there is a sampled signal, it can be denoted like this. So xk is the sample, is the sequence of values. These values are for your k less than 0. So these are the initial conditions which are assumed to be 0, and then there are some values which is in the time, positive time. Okay, so now the one-sided Z transform of this sequence, how it is defined? So the one-sided Z transform of this sequence is defined as a weighted sum. It is defined as a weighted sum. How? It is weighted with a value with something like this, z to the power of minus k. So each value, each xk is multiplied with this weight z to the power of minus k, and then summed over these k's, over these samples. Okay, now z is a arbitrary complex number. Since z is an arbitrary complex number, xz, the Z transform will also be a complex number. So what you are doing? You are taking a real sampled signal. What you are getting? You are getting a complex number. That is what you are doing. So this transformation gives you a complex number from a real sampled signal, real valued sampled signal. You are getting a complex number. Okay, so yeah, so after this we try to calculate the Z transform of one particular sequence. This one is important, and on the basis of this, a lot of others, on the basis of the idea of how we are actually computing the Z transform of this sequence, the other Z transforms can be also computed. So you consider the geometric sequence 1a, a square, a cube, like this, and it goes on, and the one-sided transform will be like this. So ak z to the power of minus k from k equal to 0 to infinity, and it is az to the power of minus 1 to the power of k. So az to the power of minus 1 comes inside the bracket and k is outside. So this is a series. So this is a summation of a series. So this is an infinite sum, and we know that the infinite sum would converge when this value is less than 1. The mod of this is less than 1, then it will converge, otherwise it will diverge. So this is the condition of convergence. This is the condition of convergence. So you see here the convergence is outside this circle of radius mod a. Okay, and this is the z plane. The convergence of the Z transform is outside this circle. So there, with every Z transform, basically a region of convergence is associated. So whenever you are calculating or you are given to calculate a Z transform, you should also mention the region of convergence of that particular Z transform. So this, you see, we have noted down that when it is converging, when the series is actually converging, what is its value? Its value you can compute very easily. Its value will be equals to z by z minus a. This comes after some simplification. So for k equals to 0, this is 1. So this would be this, and then you can simplify this and you will get a minus. Why this minus is coming? I guess it would be minus. So I don't remember the formula actually of. So this is z by z minus a. So this is what you are getting, and the region of convergence is this, and this is the when it is unbounded. So in this particular region, so in this particular region, this is converging sequence is to this particular number, and when it is diverging, it is unbounded. From this you can also infer about the inverse Z transform. The inverse Z transform of this particular thing would be a to the power of k, because the Z transform of a to the power of k is this. Where, however, one has to mention that the inverse Z transform would exist in this region only. Okay, in this region only. If nothing is mentioned, you must understand that one is talking about the convergent sequence only. Okay, not the divergent sequence. These are some other Z transform pairs you can look up in any standard book about how these Z transforms are calculated. It is the same way. You have to take, so whatever your thing is, suppose this thing you want to calculate Z transform of, so you have to do the summation k equals to 0 to infinity this particular thing with weighted by z to the power of minus k, and then you have to see what the summation leads you to. So this summation will lead you to e to the power of a z minus 1. So likewise all these are computed in the same manner, and each computation will also have a ROC. However, the ROC calculation is not always important. Here the Z transform, it is it is by default, it is understood that we are working within the region of convergence. Otherwise we would not get this particular values, particular x z. Okay, so this is a table, so you can look into this table and you can refer to this table also. However, for exam purpose this table will not be given to you, so you should know how to calculate Z transforms. Though there will not be so many of Z transform calculation problems are not so important also, maybe one or two can be given, but they will be easier ones. And if you remember this, this general form of calculation of Z transform, then you should be able to do any of the signals. So you can practice on your own, you can refer any standard book, there the calculation has been given also. These are important properties. There are some important properties of Z transform. The first is the linearity property, which is same as the Laplace transform also. Then this is an important property called the shifting property. This is very important, shifting property. This is utilized also later on. So if you have a sequence shifted, all the samples shifted, by n, shifted by n. So if you are having plus n, that means it is shifted in the negative, in the backward direction, not in the forward direction. And here you will get the xz as this, and if you have fk minus n, then you will have z to the power of minus n fz. So this is more important, this one is more important and more popularly more used actually, this particular property. Then there is another property which is the multiplication by k to the power of n, and this is the property, and scaling or multiplication by a to the power of k, this is also important, sometimes used. And convolution, if you have a convolution, so if you have a convolution, two signals convoluted with each other, the Z transform is basically a multiplication of the individual Z transform. So this is also a similar property from the Laplace transform. And lastly, we would talk about the initial value theorem and final value theorem. So if you want to know the initial value of the sequence from the Z transform, you can actually compute it by making Z tend to infinity in the Z transform. So that would give you the initial value of the sequence. Initial value means at k equals to 0. We have assumed that k less than 0, all values are actually 0. So for k less than 0, fk equals to 0. Then the final value theorem, if you want to know the converging value, the last value of the sequence converges to this value, you have to take limit z tends to 1. Please remember this, it is not 0 as in Laplace transform, it is limit z tends to 1, 1 minus z inverse fz, 1 minus z inverse fz. And as you know that 1 minus z inverse equals to z minus 1 by z, and tending it to 1, so this is basically z minus 1, so it becomes z minus 1 fz. But sometimes keeping the z is useful, so and this is also, there is a condition that fz must be analytic for all mod z greater than 1. Okay, so at this region mod z greater than 1, fz is analytic. That means what does analytic mean? That means for any value greater than mod z equals to 1, fz can be computed. That means it does not have an undefined value for any z greater than 1. It does not have an undefined value. Okay. So with this we come to the end of the lecture. So thank you for attending, and see you in the next one.